Hello, everyone, and welcome to this Clear EO webinar. Today, we are going to address from global observations to AI-driven insights, meteorological data in action. My name is Bente Liljaby. I'm going to be your moderator in this webinar. And with me, I have a very impressive panel of experts. The program is as follows. We will start with observations, big data, AI, and WMO, so the World Meteorological Organization, by Professor Markku Kulmala from University of Helsinki. He will address the global perspective on Earth observation and, of course, of use of AI. Then we are moving to a more local perspective, although ECMWF and Destination Earth is also serving the global Earth. But we will talk about Destination Earth, end-to-end AI stack for weather and climate. And it's Tiago Quintino, Head of Development at ECMWF, who will give us this presentation. Then we will come to talk a little bit about what we are doing in the Clear EO and on a more practical user-oriented perspective, namely the Clear EO applications. So we have applications on flooding, agriculture, and air quality, and the Clear EO coordinator from Links Foundation, Paolo Viviani, will give us that presentation. Then we are going to even more local perspectives, namely to see how AI is being used in weather forecasting. And that is a researcher at the Danish Meteorological Institute, Kamuk Christiansen, who will give us that. And then we will also have a discussion. Today it's a little bit special because we have two longer presentations, so we will actually take questions and comments after each of the presentations. So with that, the floor is yours, Markku.
And we need more information from observations to different areas like this Boreal Arctic area, Eastern Asia area, Africa and Amazonas, and also these dry areas, and all those points here are big cities. And this means that more and more data is coming. What happens to my computer? Okay, and a couple of examples how we have now already used this AI or machine learning. And for example, we have a look with machine learning methods, how this photosynthetic active radiation will be compared in different ways, how we are looking at how diffuse radiation, and then this kind of satellite results like this NDVI, how they are really working with different instruments, and how we are able to use this machine learning to help this big data analysis, and a couple of references that we have really worked with machine learning in earlier times. And okay, I will go back for a second. And this is mainly comparing different data sets and finding out also machine learning ways to use it. Other part is, of course, to look this haze air pollution cocktails in different cities all around the world. And actually in this peaks, the more red, the more death due to air pollution. And then we can also think this China gigacity idea. Actually, in this triangle from Beijing to Shanghai, from Shanghai to Xi'an and back to Beijing, lives today almost 10% of global population. And that's why this kind of data sets, this kind of understanding, using at the same time physics, chemistry, meteorology, machine learning, etc., we are able to get enough knowledge for global development, especially for global south. And the WASS is the World Academy of Science, which is Global South Science Academy. And if you think about what is today the population, you see the biggest cities last year, and then the estimation after 75 years, we see that the biggest cities are estimated to be in Africa, which means that and India also is continuing, but China is already going down, and in Europe we have very little, and actually in America not that much. That it's more or less population is concentrated in estimated to be concentrated in Africa. Okay, then what are the steps in our point of view for harmonized data and open data providers? And from beyond the state research to state of research to operational, it actually starts. Now I'm thinking that we are really not only in laboratory, we are really outdoors, measuring in atmospheric, in the real atmosphere and different environments. It means that step one is the individual instruments in single location. And then we might have the network of observations of these single instruments. Then we start to have research infrastructure, comprehensive long-term like our SMER station in Finland and several other countries. Then we could have thematic harmonized like this European research infrastructures, areas in continental scale, operational research infrastructures like ICOS and ACTRIS, global observation networks, operational service like weather services. And how we go from 1 to 7. And which are essential new variables in level 7, and in which fraction of level 1 variables will go to from level 1, like 1, 2, 3, etc. to 7. And for example, as I already mentioned, our SMER station, we are now observing more than 1,200 variables. And this is also the question that what is the after 10 years or after 5 years or after 20 years, this new essential climate variables, which is in WMO point of view quite important. And we need to have this kind of supporting and contributing structures to define those things. Define the essential climate variables like this global climate observation system of WMO thematic could be atmospheric, terrestrial, ocean, cryosphere, for example, satellite and in situ observations, or this kind of ENVI hubs like connections to European ESFRI infrastructures and their data. Prototype is in ENVI FAIR project, and European Open Science Cloud is one example. And then different activities like Research Data Alliance. And whatever we are doing, we have always barriers of information. And the main important thing is that we need to have trust. If there is no trust, there is certainly not any information going in and out. But if we have trust, we might not understand other people's data. Or there we need AI to help understanding, but we need to understand it also by ourselves. Then do we have access, or are we then able to find the discovery? And actually, I think that there are 3 points what I want to mention. Open data, open science, and open strategy even to make this kind of big data Science diplomacy is typically needed, and especially in the present world. And also we need to have scientific street credibility. And now what I see after 20 years, there will be hierarchy of stations of observations, comprehensive flagships like our SMER station. We need 500 to 1,000 of them globally. Hopefully they will be part of WMO activities. Median type of station like flux station or air quality networks. And then different low-cost sensors utilizing 5G, 6G, and after 10 years certainly 7 or even 8G networks. And then utilizing AI and developing these systems together with AI. And this open data, big data, knowledge transfer, data analysis together with AI is important. In impact point of view, there is at least this International Institute of Applied System Analysis near Vienna, Austria, which can be. And who takes the lead of all these things? And very potentially WMO is able to do it. We could have this kind of global atmospheric watch plus International Climate Atmosphere Institute like CERN in high energy physics. And what is needed if that we are able to go this within the next 20 years? We need to understand to go what we are doing. We need to have vision, we need to have capacity, which means person power and funding. And we also need to have feasible plans to make there. But if we are not having this kind of system, if any of those U, V, C or F is zero, we never go over the resistance to change. And this I have done together with former European Commission guy, Peru. But that's all today, and thanks for listening, and I'm happy to answer questions.
Thank you very much, Markku. I have questions for you, of course, and also maybe some interesting input. But I want to give the opportunity to the audience to ask you questions. And if you can raise your hand, I would give you the floor in the order they arrive. I think I will be able to do that. So please raise your hand if you have a question for Markku or a comment. You're all shy. While you are contemplating, I have a question for you, Markku. So using AI, of course, on this data is interesting. I mean, it goes without saying now. But I heard one thing is to use AI on the data itself to do analytics and better understand it. But there's also, it was also mentioned to me another aspect of AI, and that is related to the quality of the data, for quality checking. Have you also been including, that's another use, that's a way of using AI to check if your data is of the right quality. Have you discussed this as well?
Yes, we have, and this is actually something what is coming more and more, even in my own laboratory. We have so much data coming every day, and we really need to check these things. And it means that we are more or less in the beginning of this kind of analysis, but this is certainly needed more and more in future.
Yeah.
And I since it was like I said in one slide, if we start with single instrument, it's very easy typically to handle it by one student. But if we start to have this kind of thousands of variables, what we have, we need really to be double checking so many things every day, or actually more or less online, or this kind of near online, and before we can really put this to people to use it. And that's why we need to use this AI more and more in that one. This both data quality check, data. And the quality check means actually that when AI sees that there is something wrong, of course somebody need to prepare or service this instrument. But this is important aspect.
Yeah, and as you say, is big data. So one thing is, of course, the satellite data, and it may sound strange, but I feel like the satellite data we have sort of solved the formats and how we are doing it, how we are sharing it. Yes, the space-based data, which is already more or less synchronized, and we have agreements on how to share them more or less. But how about the in situ data? And those are more, they can be very local, even, local communities. We just had a discussion with the municipality of Oslo, and sometimes you need to use the call me method in order to get recognize that. But the way I see it is that the WMO has, as the organization that people are used to, so the meteorological organization are used to collaborate. Do you think that sharing these kind of more local data that not necessarily at the current stage are part of the WMO data sharing? Is that something that could be improved, you think?
This is actually the case that the traditional meteorological data is pretty well done.
Yes.
But then there is plenty of, let's say, atmospheric composition data or this kind of Earth surface data, environmental data sets, air quality data sets, etc., which are not at all yet in this kind of harmonized way. But that's why I mentioned those European research infrastructures like ICOS, Actris, Eltera, which are in principle doing this. And they start to be this kind of some kind operational, but not at all that level that WMO is. And this is one of my vision. I like to promote that this kind of from step 1 to step 7 in my one slide, that we really start to understand what we need to have in step 7, which is part of like WMO operational data sets, which is then available in principle for everybody. And then if it's only somebody's private computer, it means that it's not available to anybody.
No, exactly. And it's the call me. That's the call me method. Yeah. I don't see any more hands. Come on, you guys. You have this nice opportunity here to ask Markku about meteorological data. I don't see anyone. People are shy.
But this is, I mean that I also give so much information in very short time window.
Yes.
But you are welcome to also, I will send to Pente my slides, and you are welcome to ask me later, send me an email, it's totally okay. And but remind me that you have heard me today.
Yes.
That I know that in which connections you are asking me something.
Yes, I will, Markku. Thank you so much. Thank you
very much. And I will now say goodbye to you since I need to go.
Okay.
And then but anyhow, I sent my email, my slides to you.
Thank you very much. Thank you very much.
Okay, thanks. Okay, bye-bye.
Bye-bye. And the next now, Tiago, I think you are with us now, right? Yeah. Hi, Tiago.
Hi.
Good to see you. You are going to take us more to the European, even though Destination Earth is a global service as well. So just to introduce you a bit, Tiago, before I give you the floor. So you are obviously working with Destination Earth. You are at the ECMWF. You're a designer and developer of scientific computing, HPC software, and with a specialty in processing meteorological forecast data and computational fluid dynamics. You are, of course, deeply involved in Destination Earth, and I believe you will tell us a little bit more now what you are offering to the community. The floor is yours.
Hi, I'm Tiago Quintino. I had the development, head of development at ECMWF. So I look a lot into tooling and pipelines and workflows and how we transform big data into products and so on. And today I'll talk a little bit about the challenges that we have with the AI stack in weather and climate, especially now in the presence of the revolution that is happening in meteorology with machine learning. I do work for DestinE, but today's presentation will include a lot of a wider spread, a wider view of what ECMWF does, not just in DestinE, but in other programs. Just very quickly, ECMWF, if you don't know, it's a international organization that is European, and we run operational weather forecasting 4 times a day, not only for our European member states, but throughout clients around the world. We also operate Destination Earth digital twins, and we operate 2 of the Copernicus services, and we support the 3rd one. But today I would like to talk a little bit more, if you zoom in into our workflow, what we do every day, so that you understand the scale of what we need to work with and understand how AI is going to make an impact in this, okay? So we, at ECMWF, we obtain 800 million observations a day, about 6 terabytes of data, that from which we then, using our models, we produce forecasts, which are about 500 terabytes per day in 4 bursts, so 100 terabytes every time we have a forecast. And we do product generation from this, which is what the users, specific products that the users require. And we push this out, so roughly 92 terabytes per day of products that we push out. And then it goes worldwide, 1,100 worldwide destinations. And on top of that, due to our programs in open data and so on, people also can pull data from us. So both push and pull. And then we have an archive where we archive roughly 640 terabytes per day. That's including research work and Copernicus and everything that we operate around in our data center. But there is a revolution ongoing since 2022. As you probably realize, in fact, previous speaker was alluding to this, neural networks are universal approximation systems, and given enough compute and enough data, you can learn any relationship. So the real question is, for which problems is this true? For which problems do we have enough compute and enough data that we can learn those relationships? And if you look at the history of weather forecasting and the quality of the forecasts, so here higher is better, and the top blue line is forecast ahead 1 day, and then 3 days and 5 days and so on. You can see that we were doing quite well in the evolution over the last decades and in improving more or less 1 day of quality per 10 days. But then AI appeared, and suddenly we had this big jump, and AI-based models, they provide better quality and of the forecast. And this is a big game changer, is a big step function. Not only they are more accurate, they are also faster, cheaper to run, but we need to train them. And that really, really brings us to what we are here talking today, which is that if you look at data in this new world, data is really the new oil, right? This is a famous quote from Clive Humby. And another quote that I kind of like more is that if AI is the rocket ship, data is the fuel. And in this quote is more about not really that we need data, that's kind of obvious, but that the data quality is very important. Okay, so the question really is, how do we prepare and feed Earth system data at scale for AI training? So for training, really, the issue here is the data quality and the volume of that data, right? Because we are talking a lot about a lot of data. At ECMWF, we have had an archive growth over the last years that is basically exponential. We hold at the moment 1.4 exabytes of data. That's quite a lot. That's a very rich archive from which we want to learn and use in training. We have what's basically the largest meteorological archive in the world, with an exponential data growth of around 40% year on year. All the data is indexed, all the data is accessible, and is very much active. We read from this archive about 510 terabytes per day. That's a huge amount of data movement. So the question really, I would like to invite you to look at this movie, which hopefully you're seeing, of this super high resolution simulations of the Earth that we have been doing with Destination Earth. And you can imagine that this looks like satellite picture, but it's not. This is the quality of the current resolution of the models. It's so high that we have this massive amount of data from where we can learn. But more importantly, we also have data that we have been reconstructing from the past, from observations. You might have heard about ERA5. ERA5 is a very important data set that we've been building over the last decade. It has been at the base of all this revolution of AI, is because you have a data set that is so rich, so accurate, and it's able to reproduce the weather over the last 8 decades. And people have been using it to train models. And ERA6 is coming. ERA6 will be from 30 petabytes onwards. And we need to find ways of making this data useful for users to train their models. How do we do that? We have these data pipelines that we have been building over the last decade and will continue to build, where we basically, our HPC is a big data producer. We have this primary storage of data where we put hundreds of petabytes of data. And from there, we have these data stores where people can pull the data from. And these follow very known formats. And people then are able to pull the data into their own space, into their own resources. Currently, these data services are really, really very, very sought after. We have basically 250,000 users registered. We serve 6,500 users daily, new users. And about 500,000 requests a day. So 100 terabytes per day, just to feed people who would like to access ERA5 and these sort of data sets. So these data stores are just one of the parts of how our pipeline is prepared for the serving data for machine learning. However, that's not enough. You need the receiving end. You need how the users are going to use it. And this is where we've developed over the last years in a consortium with other European countries that are our member states, this ANEMOI framework, which is a machine learning framework to prepare and learn Earth system models. And you can see here the high quality of these models. This is a comparison of our machine learning model and our physics-based model, and they have, they are very quality. The quality is very comparable, and really behind the scenes is this collaboration that is a truly European collaboration, where we have not only ANEMOI data sets, like ways to create data sets for learning, but also modules that allow people to design new machine learning models, be it based on graphs or different technologies. And then in the same ecosystem, you have ways of using those models in an inference mode in order to create an operational system. But really, the big challenge is behind the scenes. How do you feed all this data to the training process? Because you can see that you have here on the left our data stores, which are basically where the data is sitting. And then on the right, you can imagine you have an HPC center that, say, maybe in Finland, where truly the training is going to happen. And training is really an HPC job. AI training is an HPC job. You need to feed these very, very hungry GPUs with gigabytes per second of data. And you need to pull out this data from the data stores, process it, shape it in ways that are specific to the training you're about to embark on. And therefore, you need the frameworks and the software that is capable of creating basically this pipeline that brings from the data stores into the parallel file systems of the HPC, and then allows you to very efficiently train your models. So we have Anemoi for the machine learning part. But for the data preparation and shaping, we have this new ecosystem that we've been developing over the last 2 years called EarthKit, and is a community software, fully open source. We have been working on it diligently over the last years, and it's soon going to be in version 1.0 released. And it's made of this rich ecosystem of components that allow you to prepare, compute, regrid, reshape into the data sets for the machine learning. So if you look at it, what you're really doing is taking all these data from different sources, different observations, forecasts, reanalysis, IoT data, maybe, you know, even the sort of data that the previous speaker was showing, all these diverse sources in diverse formats. And we use this ecosystem with different components to bring it in, process it, project it, transform, aggregate, and allow you to then move this into systems that are familiar and interoperable with the community. Put it in ZAR, process it in X-ray, time series into pandas, export it to Anemoi, and so on. So you have a really very rich ecosystem of components that we've been building because this is what the community needs. So key messages, we have been taking the expertise that ECMWF has in these massive data sets and serving users in 24/7 operational resilience, packaging that into frameworks and software, in this case, Anemoi and EarthKit, that allows us and the community. So us, when I mean here, is really, we eat our own bread, right? With the software we are using to develop for ourselves is the same software we are offering and giving to the community, transforming these vast amounts of data into AI data sets, developing really this truly scalable training and inferencing AI stack, and then collaborating with member states and partners across Europe, really leading to these breakthroughs. And to the point that right now we have already operational, fully machine learning forecasting systems since 1 year, since February last year. It was the first operational system in the world completely based on machine learning. And you know, the future is just opening, but hopefully we are providing tools for the community to develop their own models, but also work with us and so we can learn together. Thank you very much. That was my talk. Can take your questions if you have some.
Yes, thank you, Tiago.
I hope I kept with time.
Yeah, no, this is fine. Very interesting, and definitely then drawing this picture of what Markku was craving for, right? How do we use AI? Raise your hand, the audience, please raise your hand or ask your questions in the comment. If you are too shy to take the floor, we can answer the questions via comments also in the chat. But Tiago, I have a question. We have been thus far talking a lot about making data analytics ready.
Mm-hmm.
What I believe, and I saw I was not quite sure where, I mean, do you not have to make the data analytics ready before you do the other stuff, like forecasting, modeling, you know, in your, I don't remember which one of your slides, one of the last slides you were showing, you had sort of the pipeline.
Yeah, okay, I can try to share again if you want.
Yeah.
You mean
not this one you had on
this one?
This one, yes.
Yep.
So you have the observations, and before you can do anything with them, you have to make them, you know, L0, L for space.
Yeah, absolutely. Yeah.
And then you are creating, so that's in between there, right?
Yes.
Before the forecast.
If you think about it, so one of the key things that we have done here with EarthKit is that we prioritize everything in memory, processing workflows in memory, right? So when we read from the data source as much as possible, we try to keep things in memory. So, and this is why, because this is how the GPUs like it, right? If you want to be efficient with users of GPUs, you don't go around shifting data back and forth to disk, okay? No. So where possible, we load things close to memory. All these computations we can do, we are making that developing for the GPU is like first-class citizen. So that we support from the onset computations with or CPU or with GPU. And then the idea being that you can then transform to the sort of, if you're interested in saving for posterity, etc., your analysis ready data, then you can put it in ZAR or X-array, whatever you want. But that's just your option, right? The idea here, why do we call this an ecosystem, is because each of these components is in itself independent, and you can, a bit like Lego bricks, you choose the ones you want to use, right? If you're just interested in converting data, it's fine to use EarthKit data. If you're interested in just doing interpolations, for example, we have this called EarthKit regrid, okay? Or if you're just interested in meteorological functions, how to compute some meteorological parameter, you have EarthKit Meteo. So that's the sort of composability we're trying to achieve. And you're right, when people want to analyze, they usually want in the data to be already analysis ready. But that's a choice. You could read the data directly from a source that has the raw data, right? And process it on the fly, right? Because maybe you want to process it differently this time. Have a different data set, right? Remember, we work in very large data sets. I mean, it's fine when people are working on the gigabyte sort of size of data set to copy the data, right? And having duplicate and triplicate. But when you're working with hundreds of terabytes, and I'm talking about 5 zeros more than gigabyte, duplicating data, it's not a choice, right? You have to be able to choose the data from the source, process it, and immediately put it in the format that you want, preferably thinning it, right? So this is the sort of offer we have. I think the aim here is to give the researchers and the scientists options, that they can do what they would like, not to be constrained by formats, not to be constrained by methodologies.
Right. So, but when you are talking about big data, like huge amount of data, it's typically space-based data, right? It's that you
what
are.
You mean by space-based data?
From satellites.
No, satellites is easy.
Yeah, I know. I mean,
no. Satellite data is peanuts by comparison, right? We're talking about model data, right?
Okay.
So if I go to my first slide of all, right here, if you look at the pipeline of ECMWF, satellite is 6 terabytes a day.
Yeah.
I mean, it includes other observations than satellites. The output of the model is around 100 terabytes every time it runs, and we run 4 times a day. It's the same thing. The observations that constitute ETA 5, so let's go to ETA 5. The observations that constitute ETA 5 are pale in comparison by the size of ETA 5 being 11 petabytes, right? So I'm not saying the difficulty in satellite data is the heterogeneity of the data, not the volume. Is the fact that every satellite is slightly different, right? And the processing becomes more of a software problem rather than a data volume problem. I'm not trying to diminish the work. The people who have work in satellites, they do a great work, and there's a lot of work being done to make that, but it's not a volume problem, is what I'm trying to say, right? And therefore, when I talk about creating pipelines that work in memory, mostly it's interesting for people who have to shift a lot of data, right?
Okay, yeah, so the model data, yeah, because so in GEO, the group on Earth observation, we are talking about, simplified, we are talking about space-based data, so satellite data, and in situ data, and the difference is, but in this case, so you are adding yet another complicating level with, the model data that is more, even bigger, right? But then you also have the in order to further improve the results, the more in situ data or ground truth data you have, the better it will be. So that is yet another complicating factor, right, into this.
Absolutely. Yeah. And may I go again, like to the one of the last slides? So I have here one of the things, the difficulties is, for example, IoT data, right?
Yeah.
The data from sources that are not typically meteorological data sources, right? Or if they are, for example, from a citizen network of citizen meteo stations, but the reliability is very low, right? But the sheer number hopefully compensates for the reliability, right? So treating IoT data is very different than treating calibrated instruments or satellites, right? So that's why I separate them here from observations. They are observations, but they are a whole completely different. We have a few projects with EUMETNet on it in some of our member states. Exactly how do we treat and ingest? Also, their velocity is much higher. You can every mobile phone can read pressure and temperature, right? Yes. It's not the most reliable one, but if you would be reading it constantly, just that stream of data is quite a lot, right? So it poses very different problems. Yeah.
Yeah, absolutely. And the reason why I'm bringing up this now, Tiago, is that, all this data first from the global, and now you are, of course, we need the weather is global, but we are focusing on Europe. But what it boils down to basically is that it needs to be used in a meaningful way for, on ground to solve concrete problems. Yes. And that's why this is my segue now to Paolo Viviani, our coordinator of CLEAR EO. So Paolo, he's going to give us a couple of examples, because in CLEAR EO we are developing, further some additional development of the destination Earth. So indirectly related to what you were describing, Tiago. And we are using concrete examples, applications, to make sure that it is grounded in real need. And Paolo Viviani is from Links Foundation, and he has a background from computer science. So he's also into this HPC and even quantum computing, Paolo. But he is also very much an expert on Earth observations. And I will give you the floor with that, Paolo. And you have already shared your screen, I see.
Yes, thank you very much, Bente. Thanks for being here to listen to me. I'll start from the let's say the quote from Tiago before. So the idea is to give you a brief idea on how we build on top of what Tiago and Markku presented before to have a local impact by means of localized and specific applications. And I would like to start from the quote by Tiago about the rocket fuel. So in CLEAR EO, we are also starting from the rocket fuel. So we are the idea is to start from a broad range of heterogeneous data sources, and thanks to them build a system that comprises a federated data space and innovative processing pipelines and a geospatial notification system, also thanks to ECMWF. All of these supported by sovereign compute infrastructure in order to enable applications. So applications that can deliver faster and high resolution environmental intelligence for different goals. Among these goals, we have selected 3 specific pilot applications that we're going to implement within the project. The first one is about improving our capability to forecast extreme weather event impact in urban environments, specifically for flooding. The second one is to, the goal of the second application is to enable climate adaptation and resiliency for agriculture. And the third one is about improving our capability to forecast air quality. I'm giving a very, very short overview of these applications now. The first one is about, as I mentioned, flooding in urban areas. So we're leveraging weather data, including ECMWF IFS data, both to predict extreme weather events and to trigger further analysis in case of these extreme weather events is predicted. This further analysis comprises specific a post-processor specific for flooding in urban areas, which will provide a very, very high spatial resolution rainfall prediction. And this will be coupled with the 3D model acquired from LIDAR data of the surface, and all of these will allow us to run a hydrological model that is able to very precisely predict flood extent and depth. This will help us to build an open source decision support tool that is tailored to urban areas and can make a really impact. This will be tested in the Copenhagen area and is being developed also in collaboration with the Danish Meteorological Institute. The second application is about climate adaptation in agriculture. And what we're going to do is to leverage on the data I mentioned before and coupling that with 3 separate models. One is again about extreme precipitation events, one is about drought, and the third one is about soil anomalies. And we're combining these 3 models in order to deliver results directly to farmers that will be able to use water more efficiently, to protect their crops and to reduce losses and secure the food production. This is also enabled by the fact that we have agricultural experts on boards that are able to filter the weather data we have with the eye to the specific crop we're targeting. The final application we're dealing with is, as I mentioned, about air quality. Here we are fusing together a lot of data sources from emission inventories, site data, meteorological data, into and also weather numerical weather modeling into, let's say, conventional chemical transport models. But this is also being enhanced by including satellite data products and including a machine learning models for doing this kind of data simulation and fusion, which in the end is going to improve the quality of our air quality simulations. This is going to be tested on the Marseille area. That's it. I hope I was on time, Bente.
Yes, thank you, Paolo. Yeah, the idea was to give people here a flavor of what we are doing and what kind of applications and what goes into it. So thank you very much, Paolo, for doing that. And we are going to be even more concrete. So the story here is that all these global efforts actually boils down to some concrete, also analytics for weather forecasting. And the next one to speak about that is actually from Denmark, from the Danish Meteorological Institute. And Simon, are you with us? Yes, Simon Kamuk Christiansen. He is a researcher at the Meteorological Institute in the research division there, and he is working on machine learning and from an engineering point of view. So we need all the specters. This is what I really like about that we come down to you, Simon. The floor is yours.
Yes, thank you. Yeah, so I'll probably go into a bit more technical details, but also try to give an overview of what these technologies can do in weather modeling and how we use them. So first of all, I would just briefly highlight why we're even spending time on this. So first of all, it's of course much faster once the model is trained. We're talking a few minutes, even on a laptop, potentially, versus hours for a numerical weather forecast. So once it's trained, it's really fast, which allows you also to distribute the model, to share the model with anyone in the world, even with developing nations which could not train their own machine learning model, but they could absolutely apply a pre-trained model. We've also seen, as Tiago showed from ECMWF, a very rapid development of new models and new improvements, which previously would have taken decades to reach that level of improvement. So it's really quite impressive. They're very flexible in the data that you put in and then that you output from the model. Really, it's just a matter of what training data you have available to you. For example, we could crowdsource data and use, for example, if you have the DMI weather app, it asks you if you want to collect pressure data from the pressure sensor in your phone and share it with DMI, and then we could use that for weather models. We also, when we make these weather models, we like to get an understanding of the uncertainty of the model, and we do that by making ensemble models. So we produce several forecasts, and if say 10% of them say rain, then there's probably a 10% chance of rain. But this is very expensive for numerical models, and with machine learning models, we could create however many ensemble members that we want and gain a more fine-grained understanding of the uncertainty. And it's also easier to, you can make much more frequent forecasts. So our current model at DMI runs every third hour, but the machine learning model could run as frequently as we want. Yeah, sharing models, I already mentioned that. So the first model that I'll talk about is our general machine learning weather forecasting model. So it emulates the traditional numerical weather model, and it does this using a graph neural network, so a message passing neural network. There's a number of ways to implement that, and I won't go into too much detail, but I'll just say that the main idea is that instead of having one model that needs to understand the entire atmosphere and how it all works together, it only needs to learn how each set of nodes affect each other. So we have one neural network which learns how each node is affecting the other node, the neighboring nodes, and then there is another neural network which only needs to learn how each node is updated once it has been affected by its neighbors. So it's much more limited in what each neural network needs to learn, and that also makes it very flexible. So you can place these graph nodes wherever you have available training data. So that in this case, we would place each node in each of the locations where we have a data point from our numerical model. because that's of course what we use to train this model. So we use it in a limited area modeling sense. So it has a high resolution domain, which is where we would typically run our numerical model, and then it has a lower resolution border, which we get from a global forecast, just as boundary forcing. The training data is this reanalysis data set called DANLA. So that's where we take the current the current state-of-the-art numerical model and then run that on historical observations, and this gives us 33 years of data at 2.5 kilometers resolution. So it's really quite a large data set. And the model is written in this neural LAM framework, which we started working on a few years ago. It's based on some PhD work by Joel Oskarsson. But then, we've trained this model and it's in the process of being put in operations. But we are transitioning to this Anime framework that we just heard about. So we'll be training the model, future models in that framework, and try to implement our architecture into Anime. And I would just highlight that last year we published a paper about the model that I'm discussing here. So there's more detail there if you want to learn more. But the main point is that it takes on the order of 2,000 GPU hours to train the model. Once we know the model architecture. So of course there's a lot of trial and error and a lot of hyperparameter optimization, but the final model took on the order of 2,000 GPU hours to train, and the performance is comparable, and on some parameters even better than the operational numerical weather model that we use. And I just included a case, which is a storm in 2020, just to show that it's not only performing on the root mean squared error. In average, it also performs well for these high intensity events. I'll say the model is deterministic. So one of the future things to work on is to make it stochastic, so we can make these ensemble models. Typically, we've seen that the deterministic models tend to smooth out the predictions quite a lot, and we do see that with this model as well. But I'd say it still handles this storm quite well. And just some more details here. It's we tried out a lot of different architectures, and also with a triangular or rectangular grid, and we found that the rectangular grid was best. If we compared it to station observations, to actual observations that we have from the period, then we can see that the numerical model has a larger error for 2 meter temperature and 10 meter wind for the first up to around 9 hours, where the machine learning model actually performs better with a lower error. So that's quite impressive. And then the numerical model performs better on a longer time scale, I think, which is not all that surprising. And we don't have in this data set, we didn't have the numerical forecasts longer than 18 hours, so that's why there's no comparison for several days ahead. As I said, we'll need to make ensembles put it into Anemoy. A little further down the line, we would like to have observations directly in the model, and even put some physics into the model, because we have all these physical models and understanding of the physics, and if we could put some inductive bias into the model to help it, that I think could also give quite a big improvement. Then, if there's time, I'll move on to some other applications a bit faster, but we also use machine learning for a lot of other types of models at DMI. One of them is, well, we didn't actually invent this, but we just applied the model in Greenland. So this is a model that takes the finished numerical weather forecasts and processes it to highlight areas where we have these lee waves, so gravity waves caused by mountains, which is very relevant for aviation, and it's something that the forecasters, they will need to know, so they can communicate it to the aviation authorities. But this tool really just makes it a lot easier to highlight where we might where there is a risk of these lee waves. So the model is a UNet, which takes the numerical weather forecast as input and then provides as output these maps of where the lee waves are and some features of the lee waves. So, for example, that's the amplitude, wavelength, and orientation. And this means that the forecasters at a glance can see where there might be issues and what they should communicate to the aviation authorities. The next application is something that we only just started working on. So that's nowcasting. So whereas the first model I explained was emulating the numerical forecasts, that gives it hourly resolution. But of course, if you want sub-hourly, we could try to improve that model and give it some sub-hourly data. But a simpler approach is to only give it the field that we're looking at, and then have it make a prediction based on that. So that's something like precipitation. For our traditional nowcasting, it only mostly just advects the existing clouds, but of course it doesn't take into account that new clouds can emerge and the existing clouds can disappear, which is something that a machine learning model might be able to learn, even if it's only trained on the radar image of precipitation. And we're also applying this for solar radiation, which is very useful for the energy market. So for the grid operators who need to know which solar production they can count on, and where there might be where there's a chance that a cloud could cover up an entire production facility, so they need to have some backup capacity. So that's the other field that we're trying to predict. That's for satellite-based solar radiation. And we only just started working on it, so I can't really give any more details than that. But it will probably be some diffusion models. So there are a few different ones already out there that we plan on investigating to see if we could use those for our application. But yeah, that's to come.
Thank you very much, Simon. We have a few minutes, like 10 minutes, to discuss, to ask more questions.
The question here. So the question was where we can learn more about the models that I mentioned earlier. So I probably should have put the link in the slide here, but it's on it's open source. It's all available on GitHub. So it's github.com. I can show. Maybe I should write it in the chat. It's github.com/ml/neural.
Okay, great. You are using Anemoy. Are there any of the other tools that Tiago was showing that you are actually using?
Well, I haven't actually looked at EarthKit yet, but it sounds very interesting, and I have heard about it. So I think, well, I was planning on having a look at it to see what it can do.
Yes.
Absolutely.
Okay. Now, finally, Mark, the floor is yours.
Hi, Venta. Hi, Simon. Just a quick question around, have you used any machine learning techniques to optimize things like roughness, surface roughness, for example? And if you have, how have you done it?
To optimize things like surface roughness, what do you mean?
Well, if you've got, say, wind speed in an area and the surface roughness has a significant impact on the wind speed, can you optimize the surface roughness with no measurements, for example?
Well, I mean, the model you can put in any input in that you want, right? And I don't think we put in surface roughness as a parameter.
No.
But you could certainly do that, and that I think would definitely help. I should probably also mention that the scope, the parameters that we used in this model was quite limited. So there's also some work to do to expand on that and see, for example, it doesn't have precipitation, so that's something that we want to add. But I think you could definitely add, if you have some knowledge about surface roughness, you could definitely put that in there. Otherwise, the model could also potentially learn on its own. Like, it doesn't even need the information, because if you have some learnable parameters that are grid specific, then you could have the model just learn that, okay, if in these conditions wind speed is particularly low in this specific grid point, and that would probably be due to surface roughness, and then the model could learn that feature for this grid point.
Okay, thanks. Just thinking about wind farm applications.
Yeah, of course.
Okay. Otherwise, I was thinking, Norway is quite mountainous, whereas Denmark have a more flatter topography.
Yes.
But of course, yeah, if you have, there are bumps in the surface of Denmark as well. And of course, you have the windmills. Now, I see another question. So Bukra, do you want to take the floor? You can take it.
Okay, so hello everyone, my name is Bushra and I have a question. I will just read it so we don't lose time. Since your model learns interactions through a graph neural network, so I'm curious how you think about incorporating physical constraints directly into the message pattern, because personally I've been trying to explore how to use a graph neural network model on the flat forecasting. And however, it was just kind of messy results, so I stopped and I just stopped. So my question is for example, when enforcing physically consistent flow is challenging, what could be the solution? And and also want to ask how would be your approach to the trade-off? Yeah.
Yeah,
Thank
so
you.
I think enforcing these physical consistencies, I think it's very much an open question how to best do that. And I think I think we should, I think I haven't seen very many results on that field, and I'll be honest to say we haven't really started actually working on it that much yet. So I don't really know what the best way to do it is. But I know that my colleague Matthias is working on, for example, these how to represent vector features more intuitively. So, and he's shown some quite good results. I don't really know how that works exactly. You haven't had the time to sit down together, but yeah.
Okay, thank you so much. Yeah, got it.
Thank you. Thank you very much. This is very good questions and interesting to listen to even for a non-expert. It shows that when it comes down to the details, there's lots of different types of expertise and still experimentation, as I can hear. Do I see more questions? No hands raised either. No. Then I think we will close. Oh, well, yes. Mushin Ahmad, you raised your hand. Floor is yours.
Ciao, Binti. Ciao. Okay, so my question is for Simon. Can you hear me, guys?
Barely.
Okay, so my question is that sometimes using deep learning models, we use parameters that we deem that these are important parameters to be used. But using in the model tells us that these parameters are not important and it ignores the weightage of those parameters. For example, someone talked about the surface roughness or curve number if we talk about. So how we deal with these things?
I think I couldn't quite hear it. Could you speak a little louder?
Oh, okay, wait a minute. I disconnect my. Okay, so deep learning models, sometimes we use parameters that we seem to be important to us in the physical models, like surface roughness or curve number, which are important. But using deep learning models, the model tells us that these parameters are not important, and it ignores its weightage. So how we deal with this?
Yeah, that's a good question. So what we did in the paper is we did some ablation studies. So we removed some variables one at a time to see which one affected the model the most. And the ones that didn't negatively affect the model when we removed them, it's probably fine to remove it and keep the model smaller. But yeah, I think it is probably difficult to know ahead of time which parameters will be important and which won't, because the model might be able to see some correlations that we didn't expect. So I think for what we did, it was probably mostly just trial and error to train one large model and then try to make it smaller and smaller and see when it breaks.
Okay, I got it, idea. Thank you.
Okay, thank you. Okay, so I was going to ask. I see that we are 1 minute after over the time now, but for in Clerio we have urban flooding, so extreme weather and no casting is something that would be useful. So do you see that? So you are doing the weather modeling, but did you say that you didn't include precipitation in your modeling as of yet?
That's right. That was well, but first of all because it's difficult, but also because we didn't have the data available at the time. It wasn't in the first version of the reanalysis dataset, but
Okay.
we definitely want it in there. Yeah.
Okay, so it could be the next step, and that will fit very well with the applications in Clerio.
Yes, absolutely.
Yeah, so thank you very much. Thank you all. I just want to alert you to the next ClearEO webinar that will take place on the 30th of April, on the Thursday at 3 o'clock, as the same as this one. And then we also have one on the 28th of May and on the 25th of June. But so the next one will be about agriculture and climate impacts. And of course, weather and meteorology is always a component. And so then we will focus a little bit more around the climate resilience on agriculture that Paolo was briefly introducing you to. And then later in May, we will address then and talk more about the air quality applications. And finally, in June, summertime here on this part of the hemisphere, we are going to discuss a little bit more on how to integrate citizen science and the role that they can play in making better applications. So that's the plan, and you find it. I shared in the chat already a link to this webinar, and there you will see actually the timeline and a list of the date for the other webinars as well. Otherwise, I encourage you to follow us on LinkedIn and on Facebook, and of course, visit our website how often you can. And with that, thank you so much for now. Until the next.